Hello, this is our group's Physics 212 project presentation by Sean Olea, Eryn, Hume, and Seamus, Washburn. For this project, our group decided to do problem number 1. The objective of problem number 1 is to determine the angular speed of the turntable. The other aspects of the turntable system are the mass of the box that is sitting on the turntable, which is represented by big M. The radius of the turntable itself is represented by big R. The box is attached to a string that slides through the pulley, and the string goes down a hole in the middle of the turntable to be attached to a hollow ball of mass little m. The radius of the hollow ball is represented by little r. For this problem specifically, it is important to make some assumptions about the workings of the turntable system. Our first assumption is that we are neglecting air resistance so that there isn't any effect that the air resistance can have on the angular speed of our turntable or the boxes or the ball. Our next assumption is that our string that connects the two masses together is an ideal string. Our third assumption is that the pulley is massless. Our fourth assumption is that the surface, so the turntable itself, is frictionless. And our fifth, and I would argue the most important assumption, is that the block's angular speed is equal to the turntable's angular speed. And this is because the box is sitting on the turntable, so we assumed that both objects would have the same angular speed if they're moving together. The last assumption that we have is the angle between the pulley and the rope is 90 degrees, so the angle when the rope is going down into the hole of the turntable. And we also have our coordinate system located right here just for future reference.
Here in our represent physically portion, we have our free body diagram of the situation. In this instance, we have the box, the rope, and the pulley and the hollow ball all represented in a 3D extended free body diagram, as well as all of the forces acting on the objects in the situation. We have the normal force on the box by the turntable, pointing up, resisting the force of gravity on the box by the earth, the force, and then we have the pairs, the two forces of tension, which are the force of tension on the box by the rope, and then the force of tension on the ball by the rope, and then, which will later help in our solving of the equation, we have the force of gravity on the ball by the earth, pulling it down.
First, we must gather up all the fundamental concepts of physics to understand how to set up this problem. We will use formulas about uniform rotational motion to describe the relation between the block's centripetal acceleration and its angular velocity. We will also use the formula from Newton's second law, F equals ma, and its rotational analog, net torque equals the moment of inertia times angular acceleration, and the cross product formula for torque. We can represent the net force of the ball with the force of gravity pushing it down, Fg, and the tension of this string pulling up, T. We know that the tension is the acting force that causes the torque, so we can derive the tension from our moment of inertia of the ball provided by an external source and the angular acceleration. After finding the tension force, we can plug it back into the previous equation and solve for the net force of the ball. This force is transferred to the string pulling the block due to the pulley. The tension is the main force that is pulling the block to the center, so it is contributing to the centripetal acceleration. So we divide the force by the mass of the block, big M, and plug this into rotational motion formulas to find angular velocity, to find that our angular velocity is the square root of 3 times the ball's mass times gravity divided by 5 times the block's mass times the radius of the disk.
Here we have our equation omega equals square root 3 times the mass of the hollow ball times gravity divided by 5 times the mass of the box times the radius of the turntable. And then for our plug-in number section, we decided to treat that as a sense-making to see if our answer would make physical sense. So we just plugged in a couple arbitrary numbers as well as some meaningful numbers. So we, at the top here, we put the mass of the hollow ball as 0.5. And so multiplying that times 3, you get 1.5. And then we rounded gravity up to 10 meters per second squared. And then we divided that by 5 times, and then we decided the mass of the box would be 5 kilograms. And then we researched to find what the average speed of a turntable would be. And then for that, we found that it was about 0.8 meters per second. And so we rounded that up again to 1. And that then gives us root 15 over 25, which is equal to root 15 over 5, which is equal to 0.78 radians per second. And in this instance, we can see that that does make sense because in a frictionless situation, the speed wouldn't be too fast as there's no friction. Obviously, there's no friction to slow it down or anything, but it also allows it to spin continuously, and it's not too fast that it would pull the box in or pull the ball or have the ball completely unravel all the way down to the ground, causing the box to then fly off the edge. So about 0.78 radians per second is good in this situation as well.
As you can see, the units work out because angular velocity has the units of rads per second, or 1 per second if we're looking at units. When combining all the quantities that have units, we are given 1 over time squared, which goes to 1 over time when square rooted.
So utilizing our symbolic equation, we can infer that if we increase the mass of the big box M, that the angular speed of the turntable would decrease as a result. So this is because the mass of box M and the angular speed have an inverse relationship due to big M being in the denominator of the symbolic equation. So the bigger our mass is, the bigger our denominator of our symbolic equation becomes, and the smaller our angular speed would become as a result. Our group thought that this problem on this project is most similar to activity number 1 from homework 0, and this is because both problems have an ideal string that connects two masses through a massless pulley. Additionally, both problems, there is a mass sitting on a frictionless surface, and there's a mass that hangs off the edge of a surface that is connected through the string to both of the objects. The main difference between the two problems is that the mass that is suspended in our problem has a string wound around itself, making it behave like a spool, and this did not occur in activity number 1 from homework 0. Additionally, our project problem has the masses have centripetal acceleration, while homework 0 only has translational acceleration in activity 1. So that adds a layer of complexity to this project problem. So this centripetal acceleration of the turntable and the angular acceleration of the ball created that new layer of difficulty. Our group was able to utilize the relationships between translational velocity and centripetal acceleration to overcome this difficulty in the end. Thank you for listening.